This morning I'd like to resume talking about Euler and Taylor methods. You'll recall that we have a sample problem that we've been using. The derivative of y with respect to t is t cosine t plus y over t. Also, we require that when t is equal to 1, y should be equal to sine of 1. And we want to solve this equation on the interval for t being between 1 and 6. As always, we start off with a problem whose exact solution we know, which in this case is y equals t sine t. For notation, when we write y with a subscript I, or y evaluated at ti, we mean the exact value of the solution at that time value. On the other hand, if we're talking about what comes out of one of our numerical approximation methods, we'll use wi instead. Our programs produce w values, but not y values. In the programs that we're going to write, it's useful to be a little bit clever. I'm going to create a variable in my program called d1, which means the first derivative of y at the current point. The second derivative can be computed by using the product and quotient rules. When it comes time to do the derivative of y, don't actually write down the expression for it, just write down d1 instead. By doing this, we get a reasonably nice looking formula for the second derivative. There's nothing stopping us from calculating the third derivative using our abbreviations from before. It's beginning to get a little tedious though, but eventually we arrive at an expression for the desired derivative. You could go on if you wanted to, calculating the fourth and fifth derivatives and so on, but obviously things are going to get very tedious after a while. It would be nice if we could have some way of getting the accuracy of these Taylor methods without having to actually do any derivatives. Towards the end of this discussion, I'll show you various pieces of code to do these things, including what we're about to talk about. We've spoken briefly at other times about partial derivatives. That's going to become relevant now. The right-hand side of my differential equation for my sample problem is f of t and y is t cosine t plus y over t. But for a moment or so, I don't want to think of that as being the right-hand side of a differential equation. I want to think of it as just being a function of two completely independent variables. One is named t, the other's named y, and at least for the moment, we're not going to be thinking about differential equations. Starting with some t value and some y value, I'm going to change the t by some quantity delta t and y by delta y. How much does f change? If we're thinking of t and y as being completely independent variables, then a reasonable thought is take the rate at which f changes with respect to t only and multiply it by the amount that you changed t. Also, you'll get a contribution by looking at the rate at which f changes with respect to y only, and then multiplying it by how much you change the y. This is an extremely informal version of the discussion of differentials in the third semester of calculus. If you divide both sides by delta t and take the limit as delta t tends to 0, it turns out that the total rate at which f is changing with respect to t is the partial derivative of f with respect to t plus the partial of f with respect to y times the rate at which y is changing with respect to t. Those who have had third semester calculus will recognize this as one of the several chain rules that you discussed. Now we remember that we're supposed to be solving a differential equation. If y obeys the differential equation that we started with, then df dt becomes partial of f with respect to t plus partial of f with respect to y multiplied by the f value. At first, this seems like abstract mental gymnastics that's not worth anything, but that's not true. What we have just figured out is actually an abstract version of the second derivative of y with respect to t. That's the quantity that I need if I want to do second order Taylor. Second order Taylor, written out in terms of the first derivative of y and the second derivative of y, is on the second line. Multiply out all of these quantities and you'll get the last formula on the page. Again, this doesn't seem like it's very good because we have to do all of these partial derivatives. We're going to be extremely clever about this. We're going to have a new class of methods. wi plus 1 equals wi plus a constant alpha times delta t times f, but f is not evaluated at ti/wi. We evaluate the time at ti plus some number beta, and in the y slot, instead of putting wi, we put wi plus gamma. If you were to let alpha equal 1 and beta and gamma both equal to 0, you would have Euler's method again. But this class of methods contains many, many more methods than just Euler. It's likely that one of those, at least, is much better than Euler in some sense. Take the formula for the new method and expand it using basically first-order Taylor series, which we have just talked about a few moments ago. You get wi plus 1 is approximately wi plus alpha delta t times fi plus f sub ti beta plus f sub y at time ti times gamma. If you multiply all of those quantities out, you get the last line involving the w's. Now we'll be clever. Look at Taylor 2 and look at this formula. And look back at Taylor 2 again. If you make alpha equal to 1, then both of these expressions have a term of delta t times fi. Look at the next term, the one with the partial derivative of f with respect to t. The coefficient of that is 1/2 delta t squared in Taylor 2, and is alpha beta delta t in the expansion of our new method. I can make those terms match up as well. If I pick the delta t times 1/2, if I pick that quantity to be beta, we've matched those quantities as well. The term in Taylor 2 that contains the partial of f with respect to y has coefficient 1/2 delta t squared, that is. In my new method, I have alpha gamma delta t. If you pick gamma to be 1/2 delta t times f number I, those terms will match as well. Writing out our method again using the values of alpha, beta, and gamma, we get this method. Very roughly speaking, we expect this to be on a par with T2, second order Taylor. In this part of the discussion, I want to look at actually coding these methods up and seeing how they act. We will use the same test problem that we've used before. I'm going to look at Euler's method, second order Taylor, third order Taylor, and also this new method that we've cooked up, which I'll call Runge Kutta 2. So first things first, we need to talk about infrastructure. All of my programs are going to have the same basic structure. We will say implicit none. In steps is going to be the number of steps that I'm going to use in my numerical approximation method. My time values will start at n0, at t0, and go up to tn steps. The w values will be the computed approximate solution to my differential equation at the given time value. T and y are local temporary variables. F is the name of the function that gives me the right-hand side of the differential equations. Actual is the routine that computes the exact solution. I'm going to have floating point numbers a and b, which represent the smallest and biggest t value that I'm interested in. I have to set my initial condition. W values 0 is the y at the beginning of my time interval, so that'll be sine of 1. dt is b minus a divided by how many steps I'm going to do. I'm going to have a loop index that goes from I to n steps, and I'll just go ahead and calculate all of the t values that I have so that I can just refer to them. The actual work in the code here is done there. So I starts off being 0 in this loop, so I plus 1 will be 1. I'm starting with W0 and want to calculate W1. T and Y are the time and current values for my approximate solution. D1 is f of t and y. That's the derivative of y with respect to t. The Euler approximation is the old approximation plus delta t times the derivative. All of the work basically has been done now. I open some files up. The file Euler is going to contain my computed solution. Actual will have the corresponding actual solution. Euler error will be a graph of the difference between my computed solution and the exact solution, which we can do since we know what the exact solution is in this case. I print all of these things out in preparation for drawing graphs of them, and ignore the if error part. I was going to do something with that, but changed my mind. That's the end of the program. There's also f.f90. This is the right-hand side of my differential equation. There's also actual, which is a function which, given a t number, computes the exact solution. So we can compile this. In my program here, I've put all of my things in different files, just for variety. It tells me that it has created Euler, actual, and Euler error. If I want to see what this looks like, we see that even though this is an extremely simple-minded method, it's not bad. The graph of the computed solution, Euler, looks a great deal like the graph of the exact solution. Naturally, though, when we see this gap between the curves, we think to ourselves, we should add in more terms and try to get something better. This is my second-order Taylor method. Absolutely nothing has changed except for 3 lines. I calculate the first derivative, the second derivative, and then, instead of saying that the new approximation is the old one plus the derivative of y times delta t, we also include 1/2 delta t squared times the second derivative, which will be the second order term. After that, the only thing that's changed is the name of the file that I'm writing. I'm writing Taylor 2 and T2 error. So we'll compile that and run it. It created a file called Taylor2 actual and T2 error. Taylor 2. And this time, you see, the graphs are so close together that they are visually the same. They're not really the same, of course. It's just that there are only so many pixels on the screen. It might be informative to look at the errors in Taylor 2 as opposed to the error in Euler. As you can see, the error in the Euler method at its worst is gigantic compared to T2, the second-order Taylor method. That is to say, the error in T2 is much smaller than the error in the Euler method, which is what we wanted. That's what we wanted to happen. The last of these Taylor methods that I'll look at today, we compute not only the first derivative, of y, but the second derivative and the third derivative based on our formulas. 6 is 3 factorial, that's where that comes from. And again, other than the fact I'm changing the names of some of the output files, nothing else has changed. The graphs are going to be identical visually now. As we expect. If you look at the error for Taylor 3, versus the error for Taylor 2, you see that what you get is pretty much what you expected. The Taylor 3 error is much, much smaller than the Taylor 2 error. So roughly speaking, T3 is to T2 as T2 is to Euler. We should regard this as extremely good news. Everything is working the way we think it should work. And lastly, once again, very little has changed here. This line implements the approximation to Taylor 2 we got by doing abstract power series. Notice what's going on and what's not going on here. I have to calculate an f value, but that's no problem because that's the right-hand side of my differential equation. The alpha turned out to be 1, so it's the old approximation plus 1 times delta t times f. I have to evaluate the first variable at the current time plus delta t over 2, and the second one at y plus 1/2 times the right-hand side of the differential equation times delta t. The right-hand side of the differential equation, though, is just f. So that one line implements all of that work that we did. It created a file called RK2 actual and RK2 error. RK2 is supposed to approximate Taylor 2, so if I want to compare two things that are supposed to be extremely similar to each other, I'll compare RK2 with Taylor 2. Visually, they are indistinguishable from each other. They're not the same, of course, because one of them is an approximation to the other one, but at least on this particular example, RK2 and T2 produce virtually the same values. In an upcoming discussion, we'll talk about Runge Kutta 4, and then we'll begin looking at multi-step methods. In the meantime, I hope everyone's having a good day. I'll talk to you again soon.